Question 11. A student uses the apparatus in figure 8 to obtain the data needed to calculate the specific heat capacity of copper. In this diagram, we can see the power supply, a joule meter after it, and that is connected to an immersion heater that is in a copper block, and the copper block also has a thermometer. We had done this experiment as a lab report. So reading the rest of the question, the initial temperature of the copper block was measured, the power supply was switched on, the energy transferred by the heater to the block was calculated, the temperature of the block was recorded every minute, the temperature increase was calculated. Let's move on to the questions now. Question A. 35,000 joules of energy was needed to increase the copper block from 25 degrees Celsius to 60 degrees Celsius. The copper block has a mass of 2 kilograms. Calculate the specific heat capacity of copper. We should start off by writing the equation for heat energy, which is Q equals mc delta theta. Now the question has asked us to find the specific heat capacity, which, let me remind you, is represented by the letter C in the middle. So to get C subject of the formula, we have to move the m and the delta theta over to the other side. So that would look like C equals Q divided by m delta theta. And now we can simply plug in the values. So Q, which is the heat energy, is 35,000, m is 2 kilograms, and the change in temperature, delta theta, was from 25 to 60. So 35,000 divided by 2 times the difference between 25 and 60. Plugging all of that into the calculator, we get 500 joules per kilogram degrees Celsius. Question B. This experiment does not give the correct value for the specific heat of copper. Suggest 2 reasons why. So firstly, there is no insulation, so the heat could have escaped to the surrounding air. As we saw from the diagram, there is simply a copper block without any insulation. No insulation at the bottom, or the sides or the top, so heat could have escaped by conduction, convection, or even radiation. Secondly, the diagram, or those steps, do not indicate that there was any oil put between the metal block and the heater, or the metal block and the thermometer. As we had said when we did the experiment, the oil would be important to ensure that there is perfect contact between the heater, the thermometer, and the metal block. If this oil is not used, then there will be air instead, and as you know, air is an insulator. So it would prevent the transmission of heat between the heater and the metal block, and also between the metal block and the thermometer. So you would not be able to read the temperature correctly. Question C. A new design for a kettle allows the water to stay hot for at least 2 hours after boiling. 1. The energy transferred from the water in the kettle to the surroundings in 2 hours is 46,200 joules. The mass of the water in the kettle is 0.5 kilograms. The specific heat capacity of water is 4,200 joules per kilogram degrees Celsius. The initial temperature of the water is 100 degrees Celsius. Calculate the temperature of the water in the kettle after 2 hours. So once again, this question is about being able to use the equation for heat energy and arriving to the missing variable. So first things first, we have to start from the equation. Q equals mc delta theta. Now we have to get delta theta to be subject of the formula. So I have to send m and c over to the other side. This will leave us with delta theta equals Q divided by mc. Now from the question, we have values for Q, which is 46,200 joules. We have a value for the specific heat capacity of water, which is 4,200 joules per kilogram degrees Celsius. And we have a value for the mass of the water, which is 0.5 kilograms. So plugging in all these values, we get 46,200 divided by 0.5 multiplied by 4,200, and that gives us 22 degrees Celsius. Now, we have been told that the initial temperature of the water was 100 degrees Celsius. And as we know, as time passes, the temperature of water in a kettle is going to decrease. So it will go from 100 down to... Now we know that the temperature decrease in this case was that of 22 degrees Celsius. So to find the temperature of the water after 2 hours, all we have to do is 100 minus 22, which will give us 78 degrees Celsius. Moving on to part 2, the electrical energy input is 1750 joules. The kettle is 60% efficient. Calculate the useful thermal energy needed to boil the water. Now we've learned an equation, which is efficiency equals the useful energy output divided by the total energy input multiplied by 100%. Now in this case, we have to do a bit of a subject of the formula because we want to find the useful thermal energy, not the efficiency, because the efficiency has been given to us as 60%. And we know the energy input is 1750, so we can simply do subject of the formula and get the answer. What I will do now, to make sure it fits on the screen, is I'm going to shorten the text of the equation so that it is more manageable on the screen. So the equation is going to look like this. So efficiency equals useful output divided by total input multiplied by 100%. So getting useful output subject of the formula, the equation will look like this. Useful output equals efficiency multiplied by the total input divided by 100. Filling in the values, we would get 60 times 1750 divided by 100, and that will give us an answer of 1050 joules. Question D. Freezer compartments are found at the top of a refrigerator. The temperature of the air inside the freezer compartment is minus 5 degrees Celsius. Explain in terms of density of particles how the air inside the fridge forms a convection current inside the fridge. So as we had said, convection currents happen because of a change in density of a fluid. And all of this happens because as fluids get colder, they contract. If they contract, their volume decreases, and if their volume decreases, their density will increase. We also know that things with larger densities fall to the bottom, and things with smaller densities rise to the top. So since the freezer compartment is at the top, that is going to cool the air around it, which will contract, which will decrease in volume, which will increase in density, and that air that has been cooled will fall to the bottom, and it will be replaced by warmer air at the top, which will then be cooled by the freezer compartment, and the cycle will repeat, creating the convection current. So, the air closest to the freezer compartment will cool down, which causes it to contract, reducing its volume. Since ρ equals m divided by v, which means density equals mass divided by volume, as the volume decreases, the density will increase, and colder air with larger density sinks to the bottom, and is replaced by warmer air with lower density. This warmer air is now closer to the freezing compartment, so the process is repeated, creating a convection current. Question E. The diagram shows the structure of a vacuum flask. A vacuum flask is designed to reduce the rate of energy transfer by heating processes. Describe and explain how the design of a vacuum flask keeps the liquid inside hot. Okay, so we have a diagram on the right, and all the different parts are labeled. Plastic cap at the top, double-walled glass container, hot liquid in the middle obviously, a vacuum between the layers of the double-walled glass container, and silvered surfaces on the inside of the glass and also on the outside. Question E1. Conduction is reduced by the double-walled glass container that has a vacuum inside it, since both layers of glass prevent conduction, as does the vacuum layer trapped inside the glass layers. Question 2. Convection is reduced by the plastic cap at the top, since it prevents the air inside that has been warmed by the warm liquid from escaping and being replaced by colder air, requiring the warm liquid to lose heat in heating up that new air. Finally, radiation is reduced by the silvered surfaces of the glass container, since silver shiny surfaces are very bad at both absorbing and emitting heat by radiation. That concludes question 11 and also concludes the exam paper for last year's annual exam.